This is review video 40, Dissolution and Entropy. So we talked already about dissolution and enthalpy. We talked about that in the lab. I talked about that in the previous video, but we really haven't talked about entropy and dissolution yet. Most of the time, 90% of the time, dissolutions are going to have a positive entropy value, meaning that those dissolutions are gaining chaos or gaining disorder over time. And if you look at it chemically, if you look at the dissolution of sodium chloride chemically, it kind of makes sense, right? Because on the left-hand side, we have a solid, and on the right-hand side, we have aqueous. So that means that our molecules are gaining disorder because they are popping off of that superordered solid and they are moving around now, right? But in addition, we have one molecule over here and we have two of them over there. So both when considering your phase and when considering your amount of molecules, we're seeing an increase in disorder as we move from left to right in this reaction. And we can see that happening in the picture down here. We can see that the solid sodium chloride here is super ordered. It's alternating positive, negative, but as that ionic solid dissolves, we can see our chlorines are up over here moving around, our sodiums are up over here moving around along with the water molecules. So we are gaining disorder, right? But that's not every single instance. Some dissolutions actually have a negative delta S value, meaning they're gaining order over time or losing disorder over time, which at first glance doesn't seem like it makes sense because when you dissolve something, you are naturally breaking it up. One thing is becoming 2 or 3 or 4 or however many dissolved ions. So how then could a dissolution have a negative delta S? And it's because sometimes the dissolved solute can actually force order on the solvent or the water that it is dissolving in. And so if we look at this picture over here, we can kind of see what's happening. This thing in the middle is our dissolved ion. And we can see all of the intermolecular forces that are attracting the water molecules to that dissolved ion. And every single dissolution has some IMFs that form around the dissolved ions. But with certain ions, particularly those with higher charge magnitudes, +2, +3, +4, they can create something called a solvation shell, which is what you're seeing here, with those waters that are organized around the dissolved ion. But not all organized water molecules are the same. With our lower charge magnitudes like +1s, those waters, they have attraction to the dissolved ions, but they still kind of move and cruise around and switch between ions, whatever. But the higher your charge magnitude is, the higher your attraction between those waters and the ion is. And so when you get this solvation shell, those waters are kind of locked into place around that dissolved ion. And the entire complex, that entire solvation shell can move around. However, those waters that are immediately surrounding the dissolved ion don't really move around as much. And so what you've done with something like that is you've created a little bit of order in your solvent. Whereas with our normal dissolutions, that doesn't tend to happen as much. So you can still get a negative delta S even though your solute split up, even though you've created more dissolved ions. Since you've created some order within your solvent or your water, you are still yielding a negative delta S. All right, so let's talk about dissolutions and favorability now. Dissolutions with positive delta G values will not work under whatever given conditions surround them, meaning you can dump that ionic substance or that covalent substance into water all you want, but it's not going to dissolve. But when that happens, you can fix that problem. You can force something to dissolve even if it doesn't want to. And the way you do that is really the same way you would speed up a chemical reaction. You could heat something up to get it to dissolve. You could shake or stir to encourage dissolution. You could increase the pressure surrounding that dissolution, or even you could grind up the solute, so think like sugar cube versus granular sugar, to encourage a dissolution. Basically anything you would do to increase a reaction rate, you could use to increase a dissolution rate or encourage dissolution to happen in general. Because remember, just because something has a positive delta G value under the given conditions doesn't mean it always has a positive delta G value. If you switch up the conditions, like changing the temperature, which is in the formula, delta G equals delta H minus T delta S. So if you increase the temperature, you can change the conditions and make that delta G value negative overall. So remember, just because something isn't spontaneous right now doesn't mean it's always non-spontaneous or not favorable. You can fix it by altering your conditions. If you have any questions, please feel free to let me know.